We will continue our study with vertically and horizontally shifting graphs, this time focusing on how the graphs of y equals f of x compares to the graph of y is equal to f of the quantity x plus h and y is equal to f of the quantity x minus h. Let's start with an illustration. We want to graph f of x equals x squared and then graph 4 different functions and compare how its graph relates to the graph of the original function. I want to graph f of x equals the quantity x plus 3 squared, y is equal to the quantity x plus 1 squared, and y is equal to the quantity x minus 2 squared, and lastly, y equals the quantity x minus 4 squared. Now in Desmos, I want to look at the graph of y equals x squared, which I have shown, again, that parabola through 0, 0, and look at the effect of adding or subtracting a number from x and then squaring. The first example is f of x equals x plus 3 quantity squared. When I graph this function, notice that it is the same exact shape, right? So it's a rigid transformation. It's like we picked up the graph of y equals x squared and shifted it left by 3 units. Right now this graph goes through negative 3, 0 as its vertex. And then the point 1, 1 now goes through negative 2, 1, negative 4, 1. So all of the x values have shifted left 3 units or decreased by 3. When we look at the graph of f of x equals the quantity x plus 1 squared, notice that our main parabola goes through 0, 0, but this new graph goes through the point negative 1, 0, which is left 1 unit of the original graph. So we obtain this new graph by shifting the graph of y equals x squared left 1 unit. Then when we look at y equals the quantity x minus 2 squared, notice that this graph goes through the vertex of 2, 0. So every point on this graph is obtained by shifting the original graph right 2 units. And then the last one, y equals the quantity x minus 4 squared. This is a parabola that goes through the point 4, 0. So it is the graph of y equals x squared shifted right 4 units. So when there's an inside change to the x, the resulting effect will be that it will shift that original function left or right by that number of units. So to recap, the graph of y equals x plus 3 quantity squared is a graph of f of x equals x squared shifted left 3 units. The graph of y equals x plus 1 quantity squared is a graph of f of x equals x squared shifted left 1 unit. And then y equals the quantity x minus 2 squared is a graph of f of x equal to x squared shifted right 2 units. And then y equals x minus 4 squared is a graph of f of x equals x squared shifted right 4 units. So if we have a plus 3 and went left, plus 1 and went left, minus a number both went right. So the inside change is impacting the x value, which is shifting it left or right. So let's apply that here. We have f of x equals the square root of x. We want to graph each function and state how it relates to the graph of f. Our function is g of x equals f of the quantity x plus 5. Well, remember to do f of anything means I'm going to replace x with the expression that's inside parentheses. This would therefore be the square root of x plus 5. Now the domain of this function, remember, is that x plus 5 has to be greater than or equal to 0, or x is greater than or equal to negative 5. So my x values that I can plug into this function, it has to be -5 or larger. When I find g of -5, I get the square root of -5 plus 5, which is the square root of 0 or 0. Plugging in -4, the square root of -4 plus 5 is the square root of 1 or 1. If I plug in 3, the square root of -3 plus 5 is the square root of 2, which is about 1.4. And then the square root of -1 plus 5 is the square root of 4, which is 2. So I have the ordered pairs -5, 0, which I'll plot, -4, 1, -3, 1.4, and -1, 2. And just like what we discovered with the Desmos activity, because we have a plus 5 on the inside, our graph should shift left, and that's what we see here. The graph of the square root of x is actually shifting left 5 units. So the graph of g is a graph of f shifted left 5 units. Now note in this case that all of my y values stayed the same, right? 0, 1, 1.42. The thing that changed was the x value that produced it. Let's look at g of x is equal to f of x minus 6. So because the function f is just the square root of x, f of x minus 6 is the square root of the expression x minus 6. So the domain of this function is where x minus 6 is greater than or equal to 0, or where x is greater than or equal to 6. So in my table of values, I'm going to plug in 6, 7, 8, and 10. G of 6 is the square root of 6 minus 6, or the square root of 0, which is 0. G of 7 is the square root of 7 minus 6, which is the square root of 1, or 1. G of 8 is the square root of 8 minus 6, the square root of 2, which is approximately 1.4. And then the square root of 10 minus 6 is the square root of 4, which is 2. So on the graph of g, we have the ordered pairs 6, 0, 7, 1, 8, 1.4, and 10, 2. And so here we see that we have the same shape to our graph, it just shifted right by 6 units. So the graph of g is a graph of f shifted right 6 units. And again, that coincides with what we saw earlier. We have the graph of y is equal to f of x plus or minus the number h. This is the graph of y equals f of x shifted left or right h units. And we can state this formally as a property for horizontal translations. Let h be a positive real number, and then the graph of y equals f of x plus h is a graph of f shifted left h units. So if the point xy is on the graph of f, then the point x minus h, comma y is on the graph of y equals f of x plus h. In a like manner, the graph of y equals f of x minus h is a graph of f shifted right h units. And so if the point xy is on the graph, then the point x plus h comma y is on the graph of y equals f of x minus h.